From aardvarks to anteaters, echidnas to aardwolves, there's a whole range of species that have ants and termites as the main bulk of their diets. But what does such a super specialized diet do to your skull and feeding anatomy? In this episode, we're going to take a look at some common adaptations for bulk feeding on ants and termites. Dr. X here, welcome to the Skullywag Lab, where I break down the bare bones basics of skull science. This episode comes at the request of PA Taylor 7164, who suggested a video looking at large-bodied insectivores. Now, eyes are a bit of a different story, which I'm happy to do a separate video about, but all the others mentioned here do have a similar diet dominated by ants and termites. This kind of diet is called myrmecophagy. Now, you might be surprised to find out that ants are actually a super common part of mammalian diets. A 1987 meta-analysis looked at 216 species from 43 mammal families, including carnivorans, bats, rodents, and primates. Over 80% of the species examined ate ants, and more than 60% ate termites. So it's really not that much of a stretch that some species have gone all in on eating them. The main mechanical challenge of specializing on a diet of ants or termites isn't that they're hard to chew on or anything, it's that they're really small, so you have to eat a lot of them. And these myrmecophagous animals, they go to town. Numbats, for example, can eat 20,000 termites a day. Aardvarks, up to 50,000. All this chowing down on ants must have some influence on the shape and structure of the skull. And the adaptations for ant eating are actually so consistent across different animals that researchers use them as a textbook example of convergent evolution. So what are these key adaptations? Let's take a look at some skulls. The first thing you'll notice about ant-eating mammals is that they tend to have really long skulls. But the common idea that they evolved long snouts to reach deep inside nests and mounds, that's not quite accurate. Most tunnels going through ant nests and termite mounds are too small for even the skinniest snout. And these animals rarely try to shove their faces deep inside nests. Instead, that long skull exists for one main reason: a ridiculously oversized tongue. Most mammals, including humans, have a tongue that attaches around the base of the skull, the hyoid bone, and the voice box in the neck. But in anteaters, the hyoid bones are crazy long and weird shaped, and their tongue doesn't stop there either. It reaches deep into the body and attaches all the way down at the sternum. But the real tongue champions? Pangolins. Their tongues extend all the way into the body cavity, attaching closer to the pelvis and last pair of ribs. These giant tongues come with equally giant salivary glands to keep them sticky and moist. The record for the longest tongue relative to body size in the animal kingdom, that's the giant anteater. Its tongue, at around 60 centimeters or 2 feet long, is nearly a third of its total body length. Along with the long skull and massive tongue, ant-eating mammals tend to lose or shrink parts of their skull anatomy. Both the muscles used for biting, like for example the temporalis, and also the muscles used in opening the jaw, like the digastric, are usually smaller in these animals. And that makes sense because big, strong bites aren't really needed for this kind of diet. Their teeth are also smaller than those of their relatives that have different diets, often separated by gaps called diastemata. And this is often associated with the elongation of their skulls, spreading those teeth out along the jaw. We can see smaller teeth in numbats and aardvarks here. The aardvarks' teeth are also missing an enamel coating. But some species, like pangolins and anteaters, have lost their teeth altogether, along with most of their cheekbones. Fun fact, many of these animals start growing teeth in the womb, but the tooth buds disappear before they're born. Now what's interesting is that even though the teeth are frequently smaller or lost in these species, the ants and termites they eat do still need mechanical breakdown to some degree to access more of those nutrients out of them. And the way this is done varies across different species. Some swallow sand or small stones to help grind up ants and termites in their gut, while pangolins have a kind of muscular gizzard filled with spines called pyloric teeth. Kind of like a bird's crop, but more hardcore. So if they need to grind up their food anyway, why did so many species lose their teeth in the first place? One possibility? Formic acid. Most species of ants are loaded with formic acid. Formic acid has quite a low pH, Eating a diet rich in highly acidic food can weaken the teeth, and excessive weakening might increase the risks of decay or dental disease like cavities and infections. So while selection for a long protruding tongue and a long simple skull has probably been the primary driver of tooth loss over time, the formic acid in ants could have helped lock in the loss of teeth by making them more of a hindrance than a help. An important point made in this review is that tooth loss most likely needs to be preceded by the evolution of a secondary tool that can be used instead of the teeth. So in the case of myrmecophagous mammals, a long tongue and some of these different ways of grinding their food in their stomachs probably came along before any of them had lost their teeth entirely. Something to keep in mind is that it takes a really long time to become so specialized towards one particular thing. The ancestors of anteaters split from sloths around 55 million years ago. Pangolins, they split from their closest relatives, the carnivorans, about 80 to 90 million years ago. But we do have a bunch of animals around today that can kind of guide us through the process of becoming hyper-specialized towards feeding on ants and termites. The bat-eared fox frequently eats termites, but other food groups like fruits and larger insects can take up the bulk of their diet across specific seasons. Aardwolves appear to be a little bit further along the journey, having split from all other hyenas some 12 million years ago. They use their wide tongues to lap surface foraging termites off the ground and consume large quantities of sand in the process to help break them down. As you can see, the cheek teeth in aardwolves are really sporadic and lame. Numbats have a few more teeth than an aardwolf, but they're also a lot smaller, which might make their teeth a bit more important for grinding up food. But they also have a nice long sticky tongue for slurping up those termites. Then we come along to the aardvark, which loses its front teeth during development and only has dodgy cheek teeth without enamel. However, it also has a nice long tongue. And finally, the journey to a fully myrmecophagous skull appears to be more or less complete in echidnas, pangolins, and anteaters, with no teeth, a tiny little mandible, only tiny or partial cheekbones, and of course, enormously long tongues. This kind of evolutionary pathway is an example of a macroevolutionary ratchet, a process where species evolve increasingly specialized traits that are really hard to reverse. This concept has most often been applied to extreme carnivores, like saber-tooths for example, where hyper-specialization can lead to extinction risk in the face of, abrupt environmental changes and things like that. But for ant and termite feeders, I reckon if there's one group of animals that has probably quite a low level of extinction risk associated with environmental change, it's the ones that depend on a steady supply of tough little insects that can persist through difficult times. Catch you in the next video.